Okay, so I think we are ready to go. It's a pleasure to have Martin Cederwall to speak about SL5 supersymmetry.
Okay, thank you very much. So this is essentially a small observation, a paper I wrote this summer, but which seems to be related to interesting stuff. Some people in the audience may recognize some of the details. I think Laurent has been working on roughly similar things very long time ago. So let me tell you what this is about. This is essentially an examination of what will happen if you start from things that transform under SL5, and I have bosons, I sort of bosonic coordinates. This is a vector index, SL5, not GL5, SL5. And so these are 5, these are 10. So this is a very funny assignment, but it turns out that you can do supersymmetry with it. It's sort of a downscaled version of 10-dimensional supersymmetry. Because this is part of a 10-dimensional vector, this is part of a 10-dimensional spinor, and so we just...
So we're in 5 dimensions?
We're in 5 dimensions. And it's not SO, it's SL, yeah, right. So why do I do this? There are several reasons. I will talk about, later in the talk, I will come into infinite dimensional superalgebras.
N equal 1. N equal 1 or N equal 2?
This is N equals 1. I mean, this is all I have. So if you want to call it N equals 1, yes, absolutely. Nothing more. I will have the occasion to talk about infinite dimensional superalgebras. They will be of different type. I will try to define them roughly for you as we go. They can be of Borcherds type, of tensor hierarchy type, or some interesting superalgebra called E510, which I will also define for you, which has been examined by some mathematicians, Katz and collaborators, which is sort of an exceptional thing, but turns out not so, maybe in this framework, not so exceptional. It turns up in a very natural way. I've been interested in these superalgebras for 2 reasons. I've been working, I worked for many years with what I like to call pure spinor superfield theory, and I will present that framework for you in this example. So that's also an occasion to see how that works. And there you immediately run into these Borcherds type superalgebras. On the other hand, similar algebras turn up in what I've been working on for the last 8 or so years mainly, namely extended geometry, like the stuff Axel talked about. And there, that also relies on infinite dimensional superalgebras of extremely similar type. Actually, we started out doing some work with Borcherds type superalgebras in order to determine ghost structure, etc. Then it turned out that the so-called tensor hierarchy algebras that Axel mentioned by Jakob Palmqvist are really the things you need. But why do these superalgebras turn up in every physics subject I investigate? I have no idea. They seem to be stalking me. Why do they appear in such seemingly different contexts? I will not be, so that's why I'm curious, because the superalgebras appearing here will turn out to be sort of they will be the ones appearing in extended geometry. Actually, the extended geometry where you have reduced 5 of the 11 dimensions in 11-dimensional supergravity, while the superalgebras connected to super Young-Mills in 10 dimensions is the next step where you have reduced 6. So they sort of appear in different similar settings. So I thought it would be sort of interesting to investigate the other side of this superalgebra. What does it have to do with supersymmetry? I don't see the connection, but there should be maybe some. Well, I see some connection, but it's clearly different physics. Okay. So that's another motivation would be, could I just take any funny superalgebra and let it, in some sense, define supersymmetry for me? I will come back to that question, I think. Could I take, instead of going down from E5, which is D5, to E4, could I instead go up to E6 and define a supermultiplet? I have no idea. I would think not, but anybody knows the answer? Could I do it for E6? E6 supersymmetry? I don't know. Maybe not. Well, okay. So sort of a general interest led me into this sort of peculiar thing. So we typically have a supersymmetry algebra that looks like this. Some number. This, or P, whatever you like, translations. So of course I can realize the supersymmetry generators or the fermionic covariant derivatives. I commute with them. As in terms of as vector fields. I have to get the indices right. This is just GDXR. So that's my covariant derivatives. They will anti-commute. This, I write, it looks like a commutator, but it's a bracket. It means anti-commutator, of course, in this case. It's a graded thing. So these will have an anti-commutator which gives this, but with a minus sign, and commute with the q's. Okay? So how do you investigate supermultiplets when you have this given? Well, of course, you turn to the pure spinor superfield formalism and see what you get, and then you just turn the crank. So that I will now describe for you.
So the indices M are vector indices.
1 to 5.
They have nothing to do with spinor indices.
There are no spinors here.
But there are 10 of them.
Sorry?
There are 10.
There are 10 of the thetas. There are no spinors for SL5.
So it's supposed to be a twisted form of supersymmetry in 5 dimensions?
It's related to twisting. It's related to twisting of this. I was planning to say later, but I'll say it now. This is what I will find here is actually what you find if you make maximal twist.
Just the minimal one.
Minimal twist, sorry, of 11-dimensional supergravity will be described by the multiplet I find.
Yeah. So does it mean that you're in 5 because it's simple, but you would prefer to be in 10 dimensions? dimensions? Would you prefer to be in 10 dimensions?
No, I love to be in 5.
So in a sense, it's SL. Well, Brian will talk about this on Thursday, but it's SL because you've broken SO11 by choosing a fixed element there.
So it's like being in 10 and after?
Well, so it's like being in 10, but with a complex structure.
Yes.
So it's SL5.
I understand.
Okay, I should mention I didn't say anything about real forms here. You can think about this as being real, or you can think about it as being complex, or you can, if you like, for what I do here, you could take different real forms. You could think SU5 as part of SO10. That's not really important for what I'm saying. So what I do is what you do when you do pure spinor superfields, and call this sloppily a spinor, is that you form a nilpotent operator. We can, once it's nilpotent, we can call it a Brst operator, like this. And the nilpotency is implemented by a squared, I get lambda squared, I get this twice, and I get actually precisely this expression. So I have to project out that. So there's a constraint on lambda, which looks like this. Now, what does this mean? It's very simple. Since lambda is something like this, and I take the symmetric product, which I denote this, like upside down wedge. What do I get? Well, I get a big representation, and I get this. So what I'm saying, I kill this, I only get the maximal one, and that's the same thing as to say that lambda is in a minimal orbit under SL5. That's more or less a definition. This minimal orbit actually is the space of 2 planes in 5 dimensions and the scale, if real or complex scale, depending on what you work over.
So how many components you have for lambdas?
Well, how many are there here? There are 5/2.
And do you
Plus one scale.
Yeah, so it's a cone.
And do you want Q squared equal to 0 or Q squared equal to 0 modulo some equations of motions?
Sorry?
Do you want Q squared equal to 0, strictly speaking, or Q squared
Strictly
0
speaking.
modulo equations of
No
motions?
equations of motion. They will come out from the cohomology of Q. So it's strictly 0 because this is a constraint. So lambda is constrained. This is what you normally do. So this is minimal orbit. It's completely analogous to what you do in 10-dimensional superunions. You have a spinor, you form the vector bilinear vanishes, and only the big one, the self-dual 5 form, survives. This is, well, I guess you will hear more about this. Let me not go into the corresponding construction in 11 dimensions. It's this thing is present there. Okay. So all we have to do now is to calculate cohomology of this nilpotent thing, the Brst operator. That will give you the supermultiplets. How do you do that? Let me show you a backward version of how to do it. What I want to stress is really that you can fill with that expression, which essentially is equivalent to solving some superspace equations, equivalent to, for example, in Super-Mills you have f alpha beta equals 0, etc., blah, blah, blah. And then you can just go on and see what you get. That's not very instructive. What I want to stress is that lambda, and the constraint on lambda, is really what enables there to be any cohomology at all. If lambda wasn't constrained, cohomology would be completely empty. Well, the constant, of course. So that would be trivial. And if I construct the partition function of lambda, it will tell me everything about supermultiplets. Lambda knows about super things. This is something I've learned and from primarily from discussions with Ingmar and Jakob. So let me define a partition function for lambda. And since if I multiply two lambdas together, I just get the big one. And the same thing, if I multiply any number of them together, I just get a single big representation, which is the one with send this way. So this let me introduce Dinkin labels, and let the two forms sit there. And I also introduce a level, which is the power of p. So this is a partition function for lambda. It's a very simple object. One at each level. It's completely tractable. I will come back to this one because there is an interesting duality between, and this is where superalgebras come in. Suppose I want to, for some reason, factor out something I call what the hell is this? Sorry. I must tell you a bit of simple notation. What I mean by a representation denoted by its Dinkin label is simply the sum of all. This is a definition. Symmetric, completely symmetric thing. And it's the partition function for for a set of bosons in this module.
So that VP is your symmetrizing. Yeah.
The V is symmetrizing. So if I take the anti-symmetric products, I formally write it this way, and this is the partition function for a fermion in this module, twisted by fermion numbers, because I get minus every time I have a fermionic thing, which is practical. So this is definitely, and I can multiply these together, I get one, and so these behave nicely in the way it extends. So this is just notation, which is practical, not to need, I just read it as the partition function of a boson or the inverse of a partition function for a fermion in this module. So this means I compare this one to what I would have had if it wasn't constrained. And then I do some extremely simple tensor products in SL5, which I will not tell you about, and what do I. So the quotient is simply a polynomial. What does this tell me? Well, this actually tells me it's a polynomial. It ends there. So this is just, you can do this by hand. Not complicated. This is the same as this. What does this tell me? Well, you can think of this as compensating for theta. This is the inverse of what I would get if I take a partition function for theta. And what this tells you, that this tells you something of this operator, which is the first part of this. These are sort of the holes, if you like, that enables this to have cohomology. So this is the zero-mode cohomology. I don't care about DDX. And zero-mode cohomology is Zero-mode cohomology is useful because it tells you what are the fields in your theory. They can have different ghost numbers. This will typically be Batalin-Vilkovisky type thing. You will get ghosts, fields, anti-ghosts, and you have to identify which are which. But here is the answer. So this you can also do by hand by solving this. Let me show you this in a table. So I let the expansion in lambda go that way, and the expansion in theta go this way. And what do I get? Well, of course, I get a constant. That's always part of cohomology. Zero-mode cohomology is this. I get a vector here, lambda theta. I get sorry, I think that's the vector. No, that's the vector.
These objects in parentheses, like, there are five numbers, right? Or four.
It's A4.
In the four.
A4. SL5 is A4. So these are Dinkin labels.
I mean, you have 0 and 1, and the total number is...
Do I have... Sorry,
I cannot read from here. I'm just trying to make these things concrete. In parentheses, you have some zeros and some ones. So how many numbers do you have?
4 numbers.
4, okay.
So this is a one form, this is a vector.
So you have 4 times. Okay. I'm trying to connect this to something else. It's fine.
And then it actually ends up, sorry, like this, and then it ends up here with a singlet. Already here, I can figure out what the actual multiplet will be. How? Well, this one goes this way. Add 1 lambda, take away 1 theta. The other one, which is this term, adds 1 lambda and adds 1 theta. So it goes this way. So if I find two fields which are connected, I have reason to suspect that they will sort of be connected by differential operators in the full cohomology. This is a cheaty way of doing it. You should really solve it, but it always works. And this is all linear so far. So let me call this alpha m. Let me call this Vm. I have alpha, and I have a gauge transformation for it. It's a different Gauss number because lambda is supposed to have, in some sense, Gauss number 1. So there's a gauge symmetry for that one, nothing more. That means that the invariant thing will be a twofold. And I have a vector, and you see the connection. It will be divergence free. And that will be all I get. Let me tell you one more thing. When did I start? Like 5 past or something? Yes. Yeah, good. Let me tell you one more thing, because I wanted to say how this was just a zero-mode cohomology, how I could read that off from the partition function. I mean, that's in some sense is astonishing by itself, because it already says that lambda, which is a purely constrained bosonic object, knows about supermultiplet. But let me take one more step, and so I already factored out that something which I say compensate for theta. Let me also factor out something that compensates for x if I take a power expansion, or rather say a derivative expansion in some coordinates around some point. What do I get? So then I should factor out 1 minus t squared, because it comes at the next level. And this thing, which is sort of, and do I get something like a derivative expansion in what is left? If I do, I could interpret that as the actual supermultiplet. And without actually calculating the homology, saying that the behavior of the partition function is what allows this cohomology. You compensate for theta, you compensate for x, and then sort of just multiply the partition functions of theta, x, and lambda together, and you get the multiplet. And the actual form of Q is just a way of organizing this. So what do I get? I get the singlet, of course. Then I get something which comes with plus signs, which is this. And there should be a huge plus sign in front. I equals 0 to infinity. 3 plus 2i. And there should be minus, also an infinite sum. And there you have these things. And this is also something that you actually can do by hand. It's not so difficult to multiply these into. You get not very many modules, and you can see that all reduces to the simple form on the top. So this information sits in Lambda. So what is this? Well, it's derivative. Oh, sorry. I derivatives. This is not an index. It's a number of derivatives. on V. If it's divergence free, I can only get this one. This is, I can interpret as I derivatives on a 2 form. And I think of that as the invariant, the covariant, the field strength of the alpha. So it's the gauge invariant stuff you get. So this is the content of my supermultiplet. As I said, in a derivative expansion. It all sits in Lambda. So I can read it off from the partition function. It's a funny observation. I still don't understand why this happens. Well, I do, but it's amazing, I think, that this bosonic thing in the minimal orbit knows everything about supersymmetry. I could do some other supermultiplet for you, but there are more. You can consider what I implicitly did here was to consider a field, which is a scalar. So just do expansion of a scalar field in theta and lambda, start with a singlet. I could have done some other. This is what Ingmar and collaborators call the structure sheaf. I could have taken some other sheaf. I would never imagine I would say this word in a conference talk. I must have reached some new level of sophistication. I still don't know properly what it is, but I have a hunch. Okay. So this was a demonstration. Let me talk about superalgebras a little bit. This is the Denkin diagram of SL5, bent, but you're allowed to bend them. They still describe the same algebra. What we do here is we have some fermionic thing in this module. So I will extend this diagram in that way. That is what is called a gray node. It's called gray because it has a cross through it, or you can color it, but I don't have any gray chalk. This is a node, let me call it node 0, with the corresponding Chevalier raising and lowering operators are fermionic. And that's why this is distinguished. And you have the bracket, which is actually, and this is what you would call a null root, because it has a 0 on the diagonal in the Cartan matrix. And this implies already this relation, which is non-trivial for fermionic generators. Then, of course, I have H naught, which is bosonic. This would lead to what I would call, or we would call, the Borcherds algebra extension of E4. This is the simple, and then, of course, relations with other stuff. So let me just tell you what is in here. Of course, at level 0, I always have the adjoint. In this case, I also have H0, so there's a scalar also in here. At level 1, I have the 10-dimensional representation. This is easy to see because it couples to that node. At level 2, E0 happens to be the lowest weight of this module. And this means that the, let me call that R of lambda, where lambda is sits here. This means that this one would have been the lowest weight in this module. Let me call it R on minus lambda, the lowest weight module. So that means that the big module in the symmetric product here goes away, and left is the small one, just as somewhere where I erased, just as the constraint for lambda. It goes the opposite way. The constraint for lambda is complementary to the cell relations in the algebra. So there seems to be some connection. So here is the 5 bar. And this also, I mean, here also already is some, and this is a superalgebra, so fermionic, bosonic, etc., alternating, consistent grading. So this already looks like supersymmetry. Then of course it's not the same algebra. Because it goes on forever in both directions. And those of you who have seen tensor hierarchies recognize this. So this is not there. The rest is there. And of course, this is a contragradient algebra, meaning you have same f's and e's. There is an invariant killing form, and you can the conjugate representations on the other side. Now,
it's infinite dimensional.
It's infinite in all directions, yes. It's infinite dimensional. Now it turns out, I sort of alluded already that the cell relations and the constraints for lambda are complementary to each other. So there seems to be some interesting relation, and there is a relation. I think I'm entitled to call this a Consul Duality. Is that correct?
I think so.
I think so too. Whenever you try to find out what a Consul Duality is, it seems it's not well defined. So you have the right to call anything you like a Consul Duality. The duality lies in the following. There are two meaningful partition functions, which are the inverses of one another. Depending on how I define them, I could put a conjugate over one of them, but never mind, that's not important. So this is what I said before in connection to supersymmetry. This is what this algebra, which I just took out of the hat. Why is this true? Well, essentially, one way of understanding it, which is the way I try to understand it, is that if you treat the constraint for lambda in a standard BRST formalism, this has nothing to do with the Q I talked about. It's a completely different Q. The Q for the constraint, which I just wrote down. Then that Q, that BRST operator, is the co-algebra differential for this, which is B plus means positive levels. It is identical to the co-algebra differential. In order to prove that, you need to, the only thing in order to prove that is you need to show that the Lie algebra cohomology of this positive level thing is trivial. It just contains, well, the cohomology should give you the pure spinors, essentially. So you shouldn't get any funny cohomology somewhere, then things go wrong and you would have to compensate. Then it's not the correct Q. But that's essentially the interpretation. So this was shown in general for constrained objects, minimal orbit and Borcherds superalgebras with Jakob Palmqvist a number of years ago. We were quite happy about that. How much time do I have? 10?
15.
Oh, that's even better. Lovely. So I will probably have time to say what I want to say because this is thin paper. We'll soon be at the end. Let me mention.
Sorry, just what in ordinary supersymmetry does this happen or not?
This happens not always in supersymmetry, because you need to be in a situation, this is explicitly a situation where lambda is in the minimal orbit. This is not true, for example, in 11 dimensions. It's true in 10 dimensions, it's not true in 11 dimensions. In 11 dimensions, however, there will always be some object. The question is, what is the object that it's dual to? And the object, if this is not minimal orbit, this might be something funny. In 11 dimensional supergravity, it's not even a Lie algebra because there will be a 3 bracket and a 4 bracket. But there is some.
But if you take superior Mills n equal 1 in 10 dimensions, I think it works quite well.
Oh yeah, because we have a minimal orbit. Well,
fantastic. You know, in 10 dimensions,
yeah.
But somehow, these 5 mean that we express this 16. Basically, 16 is 5 plus 10 plus 1.
Yeah.
And then that's how you twist Majoranas.
Yeah.
Something. I'm very practical on this.
Yeah.
Now, when you go on, you say, I would like to understand the superalgebras action. Twisted. There is something very funny that happens starting in 10 dimensions, which is the fact that the cohomology of S it's not as exact. Because there is, the action is a kind of Chern-Simons term, depending on, there is part of the gluino is a 5, and you can write, it has 5 components, this 5 which is here, and then you have a piece, something like chi d chi, which is invariant by itself, like a Chern-Simons form. It's not Q exact, plus Q exact terms. So you see, because usually you say, you observe that a supersymmetric action after twist can be expressed as a Q exact term, which is a funny result. So you say, it describes something topological. That is true till 8 dimensions, that the superior Mills is Q exact, that kind of Q. But when you go to 10, the superior Mills has a term which is Q invariant and not Q exact. It's a funny phenomenon, because there is a term chi d chi which is Q exact.
The action looks like this.
Yeah. No, plus something, plus Q exact term. So part of these terms can be written as Q exact terms.
I don't know.
What I say is very practical because I've really analyzed n equal 1 in 10 dimensions.
Maybe you can explain to me later.
Yes.
I know that this is the action period, but well.
Yeah. Okay.
let's say it later.
This can be decomposed.
I wanted to say some more things.
Sure.
Right, okay.
Sorry.
That's okay. let me describe, so this was B4. There is another class of algebras, the tensor hierarchy algebras, that essentially look the same. This is not always, strictly speaking, completely true. There might be some little thing falling away. Let me call this S of E4. This is a tensor hierarchy algebra, the infinite dimensional generalization of Katz, of the Cartan type superalgebras of Katz. So what the purpose with it is really to, this one wants to be symmetric around this point, but then it fails because it's actually symmetric around here. This one is really symmetric around this point. So it's changed. And what you have here, then I should have gone on one step. Here you have these modules, which is symmetric tensor and this one. So they look similar, or they look for our purposes. They may actually, these may actually be the same at positive levels. I don't think this is proven. You could also do some other funny stuff, which is called E510. The way of getting the tensor hierarchy algebra, this is work by Lisa Carbone and Palmqvist and myself, is instead of having F0, and actually not even H0, you have F0I, where I takes all these values except the node where this connects. You get these representations. This is symmetric. This is actually, the conjugate of this is the next level in B. So you make it symmetric, and this is the tensor hierarchy, this is the embedding tensor representation, or if you like, the torsion of extended geometry, etc. Let's see what we had before in the supermultiplet. We started with the vector, that one, the two form, which was the field strength in this expansion. Next, the derivative of the vector, one up, one down, but divergence free, so you don't get the singlet. And at the next level, one derivative of this one. So that's this module. So if let me draw another line here and show you E510. E510 is this module I have found, but there's a Lie algebra structure on it. And you can check that it goes on like that. Matches this expansion, derivative expansion of divergence-free vector field and a closed two form. Okay.
It's vanishing above.
Right. The funny thing is that when you throw away this one, you can't go from here to here, which means that suddenly, if you had these things above, they all fall away. It becomes an ideal, because if you try to go down, you get zero. So the definition in terms of, as a tensor hierarchy algebra of E510 would be that I include F03 and F04, but not F01. Because when I take away this node, this falls apart, and it's consistent to pick only one of the parts. If I have one of these, I get the other just by raising and lowering by E and F. I don't show you the rules. It's straightforward. So this multiplet I found is what is called E510. You can write down it very easily, and you don't see by the expressions why it is an exceptional. So P generators are just diffeomorphisms, but with volume preserving diffeomorphisms. Parameters is psi eta vectors, this chi, this chi is a closed two-form, and of course it transforms like it should with the Lie derivative, and of course the thing which always is crucial, chi psi is the diffeomorphism. It can't be anything else, and it's the dual of parameter dual of chi wedge psi. So you have to check the Jacobi identities, and they are sort of very special in this case. They rely on. So this is actually, these parameters are the multiplet. The multiplet is the E510 generators equipped, well, then we can equip them with a Lie superalgebra structure. If gamma is a bosonic closed two-form, this thing holds in 5 dimensions. And it also holds that star gamma wedge gamma, which is a vector. I just define it with epsilon, so I gets an index up. This is also, of course, a closed, a divergence-free vector. So this is the only remarkable thing you have to use. So this is one of the, there is not a series, but there is a number of exceptional super Lie algebras. This is one which people think is interesting. And it turns out naturally, it's a kind of local supersymmetry algebra, and it turns up naturally as in this. This is what I get, the most basic supermultiplet. So the last thing I will say is I will tell you that since I got this from here, and one way of stating this from level 3 is that if I take the inverse of that partition function I got there from level 3, which is without the x and theta parts, Consul Duality states, among other things, this, but this also gives I can state this in another way, which relates to infinite dimensional superalgebras, which I don't know a priori why they should be related, except they in some sense look roughly similar. It's also freely generated by the co-adjoint module of E510. So you might have thought that this is the simple object and this is the complicated one, but I think maybe it's the opposite. This is a simple one, and you can use it to tell what is inside this one. From here and up, and you have to, when I just say co-joint, I have to assign the level 3 for the lowest one, so I don't start to put it in the wrong. That will give it me. So it's freely generated, of course, by an infinite, not by a polynomial thing, but an infinite dimensional thing. So that's a theorem which comes for free. That's interesting, I think. Let me stop here. I didn't have time to talk more about E6 supersymmetry, but that's good because I don't know anything about it anyway. I think this freely generated thing is a criterion for meaningful interpretation in terms of supersymmetry, but I don't know how you determine if an superalgebra is freely generated from some level. Does anyone else know? Okay, that's it.
I have a short question. You know, when you play with that kind of things, you're very happy to have at your disposal something like Q. Q squared is 0. Then Q is often not enough to determine the equations, and there is something called vector supersymmetry, which is such that if you act on fields, basically the commutator of Q with Q mu is d mu, ddx mu, right? And then, for instance, when you write a Lagrangian which is Q exact, you get a lot of terms. But the coefficient of this term is fixed by the Q mu symmetry. Actually, the Q mu symmetry comes from the fact that the Lagrangian is Q exact. You have raw parametric invariance, and because of that, you have an undercurrent. And the Q mu symmetry is the explanation of this undercurrent. So, could you get something?
I don't know.
It would be an object Q index.
I think we need to discuss this more because I'm feeling sort of lost because I don't have, I mean, I didn't write an action for you.
No, I know.
It will start this way, and maybe next week or so we will have an action with some interaction which would actually encode the structure constants of E510. But this is not Q exact.
No, but you could add Q exact terms.
I could, but
modulo Q exact terms.
I could do that, but that's, I mean, in the BV framework, that's not interesting. That's just a field definition. So it's, I don't.
When you apply this to Lagrangian where you have fields.
Yeah, but this is.
And sometimes this term doesn't exist.
So I think.
I understand that we speak different languages.
I think you need to explain this.
I have many examples. Very interesting.
Okay.
Other question?
So I think you just answered it, but just to double check, I mean, have you written down a theory that works with this symmetry and with this multiplet, or just the beginning of this?
It's sort of, I mean, you don't want any more equations. I mean, it's sort of, I don't know if you should say off shell or on shell in this case, but I mean, there is if you want a single equation of motion, which is the divergence vanishes. And yes, you can write down a linearized action where this happens. Certainly in the component formalism, Ingmar and collaborators have done some work. You can do things which don't seem to be, I mean, there are field definitions. I think in this framework, you will more or less get a unique answer, and it will encode the structure constants of E510.
Other question from the audience?
Maybe
maybe a small comment, I guess. So sometimes the way I think about these pure spinor things is that they're generating sort of resolutions of supermultiplets which are very large. And so they have lots of nice properties. In particular, the way that supersymmetry acts is now strict because actually everything is kind of free, not only over the manifold, but over a supermanifold. So the Q's act in just some simple way, and there are no correction terms anymore at the cost of having this huge tower of fields. And another thing that happens when you do this is that the action functionals get much simpler. So I think this maybe was the confusion earlier because you were talking about the component action for 10D super Yang nulls. And when you twist this, of course, you get holomorphic Chern-Simons and the other terms go away. But I think only the terms that survive in the twist sort of show up in this resolved action that Martin would write. So he would just write for this very large superfield the Chern-Simons action. And then the fact that it twists to the Chern-Simons action is sort of automatic because you're over a supermanifold. So when you twist, it happens sort of internally. It doesn't touch the action at all.
You mean that here we are playing the game of superfields and
exactly.
things which are pure exact.
So this
trick components are just Chern-Simons because integrating is like derivation. Because D of a Chern-Simon is actually D exact.
Right.
I mean, you know, it's a Chern. Yeah, I understand. I think I see what you mean.
Yeah, so there's, I guess, there's no
pure
spinor action for this theory yet, or maybe there will be one very soon.
But it's funny because there are cases like n equal 1 in 10 dimensions where we don't know superfield formulation, right? So,
well, I guess so. You know this formulation, which is like a very big. It's not a standard superfield formulation because it's infinitely generated, right? It has like infinitely many superfields in it.
But it encodes,
But the integration measure is not the conventional.
The integration measure.
I mean, it is not truly a superfield action, okay? Because you are not integrated on the free fields, okay? Because they have constraints. So it is not really.
Well, you can integrate.
Does it mean that you have an infinite number of
The superfields are not constrained.
The superfields are constrained, but the integration takes care of the few spinors constraints. And this is essential in order to get the correct action
Yeah, of course.
in the
That's
cone.
no problem. I mean, the pure spinors lie on a cone. You integrate over that cone. It's a completely well-defined geometric object. You don't need to think about
But the measure, it is not a free measure. I mean,
no.
Well, I mean,
So it looks topological, but since the cone has a tip, you can say that you can't localize away. I mean, it's not purely topological, but things localize near the tip, and it works fine.
yeah, I'm saying it's not fine. I mean, I'm saying the integration is not the usual type of superspace action that you usually write down.
Right. It's a funny curved space. It's a Calabi-Yau space actually.
But coming back to what you said, is it possible that here you have an infinite number of auxiliary fields? Because when we talk about auxiliary field, it means finite number.
Sure.
But here you say that you might have an infinite number of auxiliary fields.
Well, in a sense, there's a finite number of auxiliary fields with cost number 0. I mean, at each level in Lambda, you have a finite superfield. But you need to keep all the cost numbers up to, or down to minus infinity. So it solves it in a sort of an
This is essentially what happens for harmonic superspace, where actually you have these harmonic coordinates which plays the role of the two spinors. And indeed, if you stick to some level, then of course you have a finite number of fields. But then if you take the whole thing, so you have an infinite.
Yes. But it's fine.
Yeah.
So it's more bosonic variables. But you can integrate over them in a well-defined way, so it's okay, and it gives you the right thing.
It means many BV fields. If you were to
off shell, it's huge number, of course. Because it's really the traditional superspace constraints is what you relax and what is implied by saying cohomology. So you have to go offshore, you realize those constraints. I think we have to stop.
Okay, so if there are no further questions or comment, we'll see again at 3:30. Have a good lunch.